which means whenever you're looking at this your y, this your x, you're looking at force here, and the internal moment in this case going this way. And the reaction force, of course, acting like this. Right? Now from here, what do we get? We will get the governing equation, which ultimately can be written as y double prime plus k squared times y equals what? 0. So when we arrive this kind of result, this is a second order differential equation for this problem. And we did this problem and we used the second order differential equation approach many times in this class so far. The other approach, which I'd like to touch a little bit now, is a fourth order differential equation. Exactly the same problem, exactly the Euler's column. Rather than considering the free body diagram like this orange circle shown here, we are looking at just a section of it. So what do I mean a section of it? What if we take a unit cell from this column? So we don't take the whole thing, we just take the cell. That means you can consider that I'm going to take only a small part, which is this. Just take this out. And we consider the moment equilibrium. So when you do that, your free body diagram becomes no longer including any kind of boundary condition or any kind of support. You only have something like this. And this unit cell will look like something like this. Right? And then you consider all the forces. External force, still X here, P. Of course, you have the reaction on the other end, like this. For this unit cell, of course, you have moments. And the internal moment acting something like this. To balance it, you still have another moment going like this. What about shear? Do we have shear? Yes, we have shear, right?
Yes.
Of course, because you have moment. In this case, of course, you have shear. And the direction of shear, you can assume that, but the positive shear, if this is positive moment in the positive shear direction, we can use what color I have. Let me try this color, purple. So this is positive shear on the left hand, well, actually at the bottom side. And the positive shear on the top side is going this way. So suppose we call the shear force, the symbol in the textbook they use is called Q, and you can call it V. Either way is fine. Just to be consistent for you to understand the derivation on the textbook, I'm going to call it Q as well. And I mean this Q and this part from here. So you're going to have the moment, which is internal moment like this. Okay. Now, to define this, we have to appreciate that this is the unit cell, which means that it actually has a dimension of dx and dy. In this direction, this is dx. That's the, looking at this way, looks like that's the height of the cell. And the width of the cell is what? It's along the y-axis. So that width is called dy, which means that from here to here, this part is dy. Now, once we have this q, but this q is only at the bottom. At the top, the value of q will be slightly increased. And this expression, this can be written as q plus dq dx, because that's the increase. That's the slope. The slope times what? Times the total distance, which is distance is dx. Of course, mathematically, you can also write this to be q plus dq. That's the same idea. But fundamentally, we start with the slope times the increment. The slope is the change of shear along the x-axis, that's dq dx. And times the dx, dx is the length that this much has increased. Now, when we do this, then we can plug all these into the force equilibrium and the moment equilibrium that way. If you start with the moment equilibrium or the force equilibrium, suppose we start with the moment equilibrium. And moment equilibrium will give also the moment, right? So here we have positive moment here, and on the top, the moment will become this. The moment becomes moment plus dm dx times dx. So it's the same concept. The increase of the moment over x, that's dm dx. So this is one value times the length, which is dx. Again, mathematically, you can also write this to be m equal m plus dm dx, just m plus dm. But we're going to need the derivatives in our formulation, so we're not going to cancel them out for now. So this is the formulation. Now what we're going to do is just simply taking the force equilibrium and the moment equilibrium. The moment equilibrium will lead us to this by taking the moment equilibrium. The moment equilibrium is where we're going to take is at the bottom side, which is at somewhere here at the top. And then we're going to get this summation of moment to be 0, like this. And we're going to write down that. So what are the moments? Suppose we take which part we're going to take? We can take at the bottom. We can take the side. And suppose we take here. Which way is easier? If you take the one at the bottom, you're going to consider the more complicated expression. So why don't we take the one on the top? That means the point of moment equilibrium, we're going to take it somewhere here. We're going to take here. There are two edges we can choose, either the bottom side or the top side. And now I choose the top side because this way I don't have to worry about this expression. This one doesn't produce any moment. And that is that is the purpose. So when I do that, the moment equilibrium becomes this. First, we have to consider the moment q, which you can say that we're going to use clockwise direction as positive direction. Then the first term is this force q times dx. So that's q times dx. That's positive moment, right? And there's also the force plus p times dy. So what's dy? dy is because it has been bended. So the distance between these two forces is dy. That means from here to here, this distance. I know the illustration doesn't really do the justice in this schematic, but the distance between the two p forces is dy. So p times dy, and this p is the p at the bottom, not the p on the top. Plus m, there's a moment here, m minus m plus dm, so we have the internal moment. This m is the internal moment at the bottom side, and the other term is the internal moment from the top side. This whole thing should be 0. Of course, you can see that this will cancel out. And that means we're going to write it like this. This will become q equals dm dx minus p dy over dx. So this is our first expression, or the first equation. Next, we're going to take force equilibrium. And we're going to say the force equilibrium in the x direction. And whichever you like, sometimes when I take the right hand pointing as a positive direction, is again, you can choose the other way. That will still be okay. Then we start with the bottom force, and that's because right hand pointing is a positive direction, the first term is negative q, right? That's the bottom q. plus the top q, and that is plus q plus dq dx times dx, and this has to be 0. So what do we have here? We have, of course, the q cancels out, but more importantly, we know that dq dx is 0. This is what we found from here. That means the change of the shear over the x in the x direction is 0. There's no change of the shear force for shear.
What happens to the dx that is being multiplied by?
Dx is not 0, so if you divide everything by dx, so what we're going to do, we're not going to find out that the q is 0. I just divide everything by dx.
All right, thank you.
Sure. And please understand that it's different. dq is 0 is different from dq dx to be 0. Because here, what we're going to argue is that because dx is not 0, so that's why we can cancel out this dx from here. This dx is canceled out because dx is not 0. So that's different from by saying that dq is 0. Please understand these two are different. Okay. Now, so this is the second expression we have. Okay. Well, if dq dx is 0, and very soon you're going to understand why would I say that. We have the first expression, which is q, and q has an expression like this, correct? What if I just differentiate the whole thing? What if I just differentiate this equation 1? So that means you differentiate the first one. Just this first equation. What are we going to get? On the right-hand side, on the left-hand side, we have dq dx, correct? What about the right-hand side? We have the second order differential derivative of m with respect to x. So that becomes d squared m dx squared. And what happens to the third term? That's just p times what? Times second order derivative of y with respect to x, right? So that becomes just d squared y over dx squared. Like this. And what do we know from equation 2? This whole thing must be 0. So this is 0. Now we look at this.